Gracias. Mi español es muy mal, pero my English is kind of okay. My name is Dan. I just flew in from Minnesota a few hours ago. So if things seem weird or crazy, it's not because WebAssembly is weird and crazy, it's because I have no idea what's happening right now. There are lights, I'm on stage. You can find me on Twitter as @Callahad. Probably not tonight because after this I'm going to go to sleep. But in the next day or two, I'll post or tweet out a bunch of links to other resources that you can follow along and learn more about WebAssembly. So, Callahad on Twitter. So what is WebAssembly? WebAssembly is a compiler target for binary on the web. It's its own general purpose virtual machine. Despite the name web, there's nothing intrinsically tying WebAssembly to the web. It just happens that it's being implemented in web browsers to start. And so now we're just going to go to demos because that's my slides. There's also a Q&A slide. But when I say WebAssembly is a compiler target for the web, what I mean is that I can take something like this cube.c file. And I want to note that this was copyright 2005. Testing. Better? Yeah. I found someone else's code to draw a spinning cube on a 3D canvas because I have never done any sort of game or graphics development in my life. And the great thing about this is written in just old school OpenGL. You set up colors and vertexes. I don't know what any of this stuff is, but it's a relatively small program. And if I compile it, I get this binary cube, and I get a spinning cube. Now, all of you here at Web Games Day, how many of you have done something like that before? Okay. Yeah, so you're all way more qualified to assess this than I am. But what's interesting about this is there's always been this divide. This is written in OpenGL, which is a cross-platform graphics library. It's written in C, which is a very portable programming language. And so I can run it on a Mac, even though this version of OS X wasn't even a spark in Steve Jobs' eye 12 years ago. And I could also compile it and run it on Windows, and I can do it on Linux. But what about the web? WebAssembly lets me take that same exact source code and if I remember my makefile, and I can say emcc, which is a separate C compiler, WASM1, output webassembly.html. And now I have a few files, a couple hundred kilobytes of data. But if I open up webassembly.html, I get that same exact cube spinning in my browser without any code modifications at all. So when I say WebAssembly is a virtual architecture or a compiler target for the web, what I mean is that we finally come up with a way to genericize the things that the browser engines are already doing in their JavaScript engines and say, let's let other languages target this as a virtual machine. So if I try to open the same demo in Safari, which does not have WebAssembly support, nothing. That's not so good. What can we do? So it turns out the compiler toolchain I'm using is actually one that started back several years ago with a project that Mozilla was investigating to replace plugins on the web. Because if you go back 10 years, there was Flash, Silverlight, Shockwave, QuickTime, RealPlayer, Unity, Acrobat, all of these other file formats, the Java plugin, all these other things that wanted other capabilities, wanted to run faster, wanted to reuse the same code, like the Adobe Acrobat plugin. They wanted to use their same rendering engine both in their desktop product and in the web. They would write a plugin. And the problem with plugins is that they ran alongside the browser. They weren't in the same content sandbox. If you fed them malformed data and they processed it wrong, then you could attack a plugin and break out into the whole rest of the system instead of just breaking the browser. And we don't have that concern with JavaScript. You go to a web page and it's going to be able to run whatever JavaScript it sends you and you trust that your browser will keep you safe. Plugins made that a lot harder. But there were many things that plugins that these other sort of native solutions were better suited for, things that required that sort of code reuse, things that needed higher performance because they couldn't afford a garbage collection cycle. This is especially important with game programming where you need consistency in your frame rate. You need consistency in signal processing. And you can't be consistent if at any point your program may stop and try to go and sweep all the memory and collect all the unused references. And so Mozilla started looking at this problem and said, all right, well, what if we can just make JavaScript fast enough to replace plugins? And we called that project WASM.js, assembly.js. And so I can make, I really should learn what my makefile targets are. So I can instead say, not include this WASM1 argument to my compiler, and I'll tell it to output wasm.js.html. And if you look, I get several files, again, about the same file size. But what WASM.js is it's a subset of JavaScript that's incredibly optimizable. It lets you opt out of garbage collection. It lets you do things like tag your variables as an integer or as a floating point number so the compiler can make optimizations ahead of time. But because it's just JavaScript, if I go and load that version in Safari, it works. So we released WASM.js, its first version, I believe in 2009. Well, that's not right. Let me check my dates. 2013, we started work in 2009. And we showed that it was possible to take arbitrary C and C++ and move it to the web. And it would work everywhere because it was just JavaScript. But you end up with these enormous files because JavaScript isn't meant to represent binary data. It's not meant to represent the sorts of constructs that exist at this lower level. And so we came up with WebAssembly as a way to shrink that down. WebAssembly is a binary format. It's supported by all major browsers. Firefox shipped with it on Tuesday this week. Chrome ships next week. Apple and Microsoft are on board. And what it lets you do is it lets you effectively take that same tool chain, find my tab, and say take any C or C++, throw it into the special compiler, which puts out WASM.js, this optimized subset of JavaScript, and then throw that through another tool that translates the WASM.js into WebAssembly. Because WebAssembly is more or less just a binary encoding of a stack machine for the web. But the great thing about that process is you have that intermediate step where you're generating that WASM.js, which works everywhere. So I could actually use a compiler that spits out both a WebAssembly and an WASM.js representation of the same program, and then checks and sees, does the browser support WebAssembly? If so, use that. Otherwise, fall back to WASM.js. And so the hybrid would work in both situations. Now you can see the hybrid, the WASM.js is about 26 kilobytes. The WebAssembly is about 15 kilobytes. So you're saving about 40% there. If you gzip them, it goes down to 8 kilobytes and 6 kilobytes. So it's about a 20% savings. But what's better is this WebAssembly is a binary format. So it can be pre-compiled, it can be pre-optimized. It can be a lot faster to load and parse because the browser isn't having to churn through 40% or more of text and do all the parsing and all the validation up front. The WebAssembly is a much nicer format for that. So now that we have this ability to go from C to the web with any other low-level language, we can start doing things that are absolutely ridiculous, like taking a standard Unity demo, and if it loads, I can't adjust the volume, so we'll make this brief, but I can go and drive my little tank around. So you can take a program that's compiled or built in Unity and say, just like you would say compile it for Linux, compile it for Windows, compile it for Macs, you can also say compile it for the web, and it runs in my browser without any plugins. And that gives me all of the benefits of the web. I have a URL. I can just link people to this game. They download, they run it. But it's also happening inside the browser's sandbox, so you know it's safe. Unity's on board. Other engines are on board. So there's Epic with its Unreal Engine has a demo called Zen Garden, which I have to compile for a second. So this is the version 4 of the Unreal Engine running natively in my browser. And it'll work on my phone, which is using a completely different CPU architecture. It'll work on my laptop, all thanks to WebAssembly. So this is a huge boon for games, and it's fully interactive. I can go and look at the fish. Let's close that. So here's the deal, WebAssembly. If you're a game developer, if you're already using Unity or Unreal, all of a sudden the web is just another platform you can target. This is huge. But it's not just about taking entire applications to the web, though that is certainly really interesting. The Internet Archive's Internet Arcade uses a WebAssembly or an ASM.js port of MAME to let you play arbitrary video games just in your browser, no plugins, nothing. So actually, yeah, see, MAME, launching emulator. And let's not do that over the speakers. So all this is in service of how do we get native code onto the web. In addition to doing these big whole application ports, you can also start viewing WebAssembly as this low-level counterpart, a complement to high-level JavaScript. So just like how you might see a major game engine written in C++, but all the logic is scripted in Lua, WebAssembly finally lets you make that same choice of, I need performance here, so I'll implement it in C or Rust or C++, compile that to WebAssembly, but I'm going to keep the things that aren't performance critical in a higher level language like JavaScript. So as an example of that, let's go to the WebAssembly Explorer. So this is a tool that Mozilla's been working on that lets you type in arbitrary C or C++ and see how it compiles to WebAssembly. So if I make a function that returns an int, let's see, half int x. Is this legible to people? Yeah. There we go. And I compile that. Over here I can see WebAssembly. So WebAssembly is a binary format, but this is a textual representation of that. And because it's a stack machine, you see here we define the function. It has one parameter, which is a 32-bit int. It returns a 32-bit int. And the first thing it does is it gets your first argument, puts it on the stack, then puts the constant value 2 on the stack, and then executes i32 divide. And then the result of that goes back on the stack, and that's what gets returned to the calling function. Now the cool thing about this is that C has type information. It knows that this is an integer. If I had instead said float here, compiled that, I get a slightly different body where instead I'm multiplying by 0.5. But what gets really interesting when you start taking into account things like being able to say this is an unsigned integer. This is never going to be negative. And this is an unsigned integer. And you can start using this type information to say, well, if I'm trying to divide an integer, and I know it's positive, if I'm trying to divide that by 2, I can just shift all the bits to the right by 1 space. And that's effectively the same computation. And so the compiler also knows this, and now instead of that div, I get the variable, I get the constant number 1, and I shift right by that constant. And this works for any power of 2. So if I do that by 16 and compile, shifting right by 4. But if I do this by 15, because that's not a power of 2, then my compiler goes back and switches to division. So this is kind of the low-level nuts and bolts of WebAssembly. because you're compiling it to this intermediate representation, which really only knows about integers and floating point numbers, 32 and 64-bit, your compiler can spend CPU cycles up front trying to optimize, trying to figure out what the most effective math is for the operation you're trying to perform. And you can then verify the optimizations it arose at. With JavaScript, you don't know when you write a function if it's going to receive only integers, if it's only going to receive positive integers. You may go through an array of 100 arguments and 99 of them may be ints, but the last one may be a float. And so every time you call a function, every time you do something in a JavaScript engine, it has to check and say, what do I think this input will be? What are my optimizations that I can make? And then are these ideas that I've made, these assumptions I've made, are they still true? Can I actually act on them? And there's overhead to that. So while a function like this implemented in JavaScript may eventually optimize down to doing a bitwise shift, you're not guaranteed to get that, like you are with WebAssembly, and you're not guaranteed to get it quickly. And every time that the function gets called, the JavaScript engine still has to check and say, is this really an int? Did I make the right optimization? That goes away with WebAssembly because it has static typing. In a way you can think of dynamic types as being a lot easier for the developer to deal with, but at the cost of being really hard to optimize for a compiler. So in this WebAssembly Explorer, I can write this function. I can then click download, and it gives me a test.wasm file. And let's see. So if I downloads, sorry, let's see. So let's go and get that open. And so how do I use this function that I just wrote in WebAssembly? So I downloaded this binary, and just to look at it, actually, so if I dump it, you can see that there's some structure to this. The magic number is a null, then ASM in ASCII. Then there's the version of what version of WebAssembly is this. Right now this is version 1. We don't plan on any breaking backwards incompatible changes, but that's there if something has to happen to the binary format. You can see in here the token half. So there's the name that we called our function is present in the binary somewhere that we can reference. But otherwise, this is a very small binary file. It's not JavaScript. It's compiled code. And I can go in my console, if I wanted to run this. Well, first I have to go get it. So let's fetch test.wasm. And then, with the response, let's turn that into an array buffer. And so, hello. So fetch is a promise-based API. It's a replacement for XHR. So I do this, it immediately returns a promise, and then asynchronously, it tries to go and finish fetching the data and returning it to me as an array buffer. So if I look at that value again, you can see that promise has gone from pending to fulfilled. If I store this as a global variable, I now have a reference to that array buffer. I can now call WebAssembly.instantiate with that array buffer. This also gives me a promise. So we don't want compilation because the WebAssembly code isn't the final representation. It still has to get compiled down to actual native machine code, which on the WebAssembly Explorer is this rightmost column. But it's really simple to translate, for the browser to translate from that intermediate representation over to the native one. But it still takes time. So when you call WebAssembly instantiate, it says, okay, I'll get back to you when I'm done compiling, but I'm going to do that in the background. So we look at it, it's fulfilled, I have an object. Let's pop that out as to a global variable. And that object has two properties, module and instance. The difference between these is similar to the difference between an exe file on your hard drive and a running program. The module is inert. It doesn't have any memory. It doesn't have any live data. It's just the program. The instance is an actual running copy of that program that has memory, that can interact with the world, that kind of exists as an ephemeral but active object. You could cache this module. After you're done compiling something, you can go ahead and say, shove this into IndexedDB so I don't have to repeat this compilation. But now on this, I can go and access it and I can say, okay, temp1.module. So that gives me a reference up to the module. temp1.instance.exports. And that has on all the things that we wrote in our C and C++ and that we marked for exposure to the outside world. And so you can see I have this function half. So if I say temp1 exports, instance exports half, it's a function. If I pass in 100, I get 50. If I pass in 50, I get 25. If I pass in 3, I get 1 because we're doing integers. This is all it takes to have a single function. If you find a function in your game or in your web app or something else that's CPU bound, this is all it takes to re-implement that in C and then call it from JavaScript and get a value back out from JavaScript. So I've been talking for a while, and this room is small enough to where I think we can have a conversation. What questions do you have right now? Does this look interesting? Do you think this will be useful for you? Yeah.
I have a question. What happens if you pass another value that is not an integer?
What happens if I pass hello? I get 0. Why? I don't know. That's something I should look into. There is, because the WebAssembly binary has static exports and imports, much like the new JavaScript ES6 modules. The browser knows what types it's expecting to send in and what types it's expecting to get back out. And if you violate that, normally, I guess, if you're running natively in C, you get a segmentation fault. But here, because there is a foreign function interface, the browser can say, well, that's not the type I expected and reject it or do something. Somehow we get 0. What if I pass 1 point? Or 100.0. So it looks like the browser's tries to coerce it to the type that it wants. Because JavaScript is dynamic, WebAssembly isn't.
Can you have a Stack Overflow, for example?
Can you have a Stack Overflow? Yes. You have a finite amount of space. So WebAssembly right now is a 32-bit, has a 32-bit address space, though it can do native 64-bit math, which is one of the things that makes the MAME port to WebAssembly actually perform well enough. But you only have so much memory and you only have so much stack space. The architecture of WebAssembly is such that when you look at many modern programming languages, so Java, .NET, you have a virtual machine that provides all of these functionalities, garbage collection, the compiler, and then it has a common set of APIs. So the Java standard library, the .NET class libraries. And those are what interact with the hardware to do audio, networking, whatever. Modern JavaScript engines look very similar, where we read in JavaScript, but then we try to compile it. We try to watch it and see what are the hotspots. Can we turn that into native code just in time? And then the APIs are the web APIs, WebGL, WebAudio, WebVR, IndexedDB. But the architecture of a modern JavaScript engine is very similar to the architecture that you might find in the .NET CLR or the JVM. And so what WebAssembly does, instead of trying to sit alongside this as a separate thing like plugins or like Google's native client tried to do, WebAssembly just sits right alongside JavaScript because that same VM is going to have to translate the JavaScript into a lower level representation as part of its optimization chain. And in many ways, WebAssembly is just shortcutting that and saying, well, here's what you were hoping to arrive at anyways, but it's already been done for you. And that means that it's still running inside the same virtual machine. It still has the same security properties as the web, and it still has the same APIs as the web. So you're still using WebGL, you're still using Canvas. The difficulty is that WebAssembly is still very new, and we don't know how to expose those APIs cleanly to WebAssembly yet, because we don't want WebAssembly to be limited to browsers. We want this to be something that could eventually be a general purpose bytecode for anything. And so you can call out to Canvas, and you saw it with the cube demo. It was rendering that cube to a canvas on a web page. But it's doing that indirectly, either through a shared array buffer or other calls where you can pass in a function reference from JavaScript, because the only arguments you can send in are ints and floats. But you could instead say, okay, here's a big shared array, and when I'm going to get a callback from you, and when I'm done, I'm going to call that callback with the offset that you should read into the array. And the JavaScript can take care of reading from there to the end of the array and putting that into Canvas or whatever else. So there are ways to get out there, but it's not very direct. But the important property is that you stay within the web's existing security model. So there shouldn't be any unique security vulnerabilities to WebAssembly. You don't have to worry about it, someone causing a segmentation fault and then getting root on your laptop. Other questions? Yeah.
Yeah, I'm thinking that you might use these for like compiling big projects, but I don't know if you have to actually compile every single time, or that stays like compiled in memory of the browser and you can reuse it again.
So the browser does try to cache the compilation, and you yourself can cache the that module. When you do the WebAssembly instantiate, you get the inert module, put that in IndexedDB or whatever else, and that can be reused over and over again.
Yeah, hello. What about other languages? Is there a roadmap, if any, for Haskell or any machine compiled languages?
So what about other languages? The initial compiler, which is called mscriptim, is a port of LLVM that has well supported C, C++, Objective-C, and Rust. Rust is coming along. There's upstream support in LLVM that's trying to build its own native support for WebAssembly. But right now, because WebAssembly doesn't have a garbage collector, that's how you can get the more consistent performance. It's harder to port more dynamic languages like Python or Ruby or Haskell or things like that to the web. But it's possible. Anything that can compile down to native code should be able to run as WebAssembly. A great example is PyPy.js, where there's no garbage collector, but you could just ship a garbage collector alongside your script. And so this is a Mozillian by the name of Ryan Kelly who wrote a few modifications to Python to let it compile to ASM.js and then output more ASM.js as you ran it. And so this will actually, I can import from test import Pystone. Main, is it? So I can benchmark, and because this is a JIT compiler, this will get up to about 300,000 of these, this benchmark metrics per second. If I try to do that natively, my native computer is actually slower than the version he wrote running in my web browser. The downside of this, because you're having to ship the entirety of the Python runtime along with it, is there's about a 5 megabyte overhead, which isn't great. But once we get to the point where you can use the browser's garbage collector, reuse that as part of your code, and if Python gets better at eliminating dead code and doing static analysis, so you can say, well, I don't need all of this library if my script's only ever going to use these sections of it, then it could be feasible to run a language like Python instead of another high-level language in the browser like JavaScript. We think viable implementations like this will take 2 or 3 years. We need to land some higher priority things, SIMD support, multi-threading into WebAssembly first, and then we're going to turn on access to the garbage collector. Other questions?
You're talking of compiling C or C++, but besides compiling C and C++ into WebAssembly, isn't writing in WebAssembly directly encouraged? Or allowed to practice, at least?
So I'm not quite sure I follow. What do you mean about encouraging it?
In the web you showed before, the WebAssembly Explorer, you could write in C++, then it would translate into, but aren't you showing directions of writing directly in assembly?
Yeah, so you could write directly in assembly if you wanted to. Just like you can today with, if you're writing C, you can do inline assembly or something like that. We think it will be more common for people to start with a language like C++ or Rust and compile down. But yeah, for a small mathematical function, sure, hand tune it. That's the beauty of having the pre-compilation phase, is you can actually go into the assembly and
I mean, it would work in any explorer that would support WebAssembly, shouldn't it?
Yes. Yeah, I mean, yeah, you have to translate from this text version to a binary, but yeah, then anything that supports WebAssembly.
And then, aren't you thinking of compiling JavaScript?
So, are we thinking of compiling JavaScript to WebAssembly?
So that you could, for example, take jQuery and make something fast, really fast.
So, we think it will be very common in the next 3 or 5 years for large frameworks and libraries to have components written in something compiled to WebAssembly. So I'd be surprised if, for instance, React or Ember, if their virtual DOM implementation didn't in the future rely on some algorithms implemented in a lower level language. But for generic JavaScript, it's the same problem as the Python version, where you would also have to ship, because WebAssembly only knows how to deal with numbers, you would also have to ship your own JavaScript runtime to the browser that would understand objects and strings and things. But your browser already has a very good one of those. All right. Any other questions? There's a microphone, and it will come to you. It's wonderful. Oh, yeah.
You just said something about multi-threading.
Mm-hmm.
Is that on the works? Is there any planning on adding that to both JavaScript and WebAssembly?
So if you go to webassembly.org, and there's a roadmap link at the top, and they just redesigned the page. There used to be a sidebar. Maybe it's over in Docs now. Oh no. Somewhere in here, additional features, here we go. So there's a list of all the things that we really want to add to WebAssembly in the short term, now that we've gotten the binary format finished. Number 1 is good tooling support. Number 2 is threading using probably using the POSIX thread model. And after that is fixed with SIMD, feature testing, and then in the future are all these other things that we'd like to do.
Okay, thanks.
Yeah, so it's, by the end of the year, we should have at least some browsers implementing multi-threading. Anything else? All right, so I will tweet out a bunch of links to a bunch of demos and other things. There's a great C++ GUI library called Oriole that does all sorts of fun things in WebAssembly. Oh, that's the WASM.js version. But you know, it'll do lots of particle instantiations, has a mesh viewer. If you want to start playing around with something that's designed from day one to compile to the web, it's a pretty fun library. Otherwise, if you're using Inscriptum, there's the EMCC show ports. Inscriptum itself, in addition to being a compiler that can go from C or C++ into WebAssembly, it also emulates a lot of the POSIX APIs. So it gives you a virtual file system that it then implements on top of IndexedDB. You can use SDL, SDL2, libpng, zlib, freetype. It has a bunch of these really common cross-platform libraries with ports that make them really seamlessly touch the web. So Inscriptum is a great place to start. Everything changed. This is not the end of JavaScript, but this is the end of the JavaScript-only web. And it happened last Tuesday. So again, I'm Calahad on Twitter. doop. And thank you so much.